I don't know, I'm not very good at drawing this. Okay, in terms of shapes and physical things I'm alright, but when I did my course at university in engineering, we didn't really spend a lot of time drawing animals. So what I have here is a pretty poor picture of a very furry lamb. Okay, now this very furry lamb is going to be one of the equations that you do need to know. And there's another variation of it. We can have a very furry lamb. We can also have a cute furry lamb. And I'll explain the importance of this in the video. Okay then, what we have here to help kind of link up the very furry lamb to a bit of Lego is a small train. And there's a very small train, maybe driven by one of these construction workers in a mine. And we also have a train carriage. And what we can think about is maybe the length of a train carriage, and also maybe how many train carriages go past somebody who's counting every second. And if you know the length of a train carriage and you know how many go past you in a second, you can work out how quickly that train is actually moving. So we have the train carriages, and what we can think about is maybe the length of that carriage, x. Okay, and this might be equal to maybe 5 meters. Okay, and we can also maybe think about the time it took for each carriage to go past. So maybe the time for one carriage to go past was 0.5 of a second. Okay, so we've got carriages which are 5 meters long, and it goes past in 0.5 of a second. Well, what we can then do is think about our speed equals distance over time equation. So speed is equal to distance over time. And the distance in this case was maybe 5 meters, and it went past in 0.5 of a second. So the velocity, in that case, of that carriage, 5 over 0.5 was equal to 10 meters per second. But what's this got to do with a wave? How does knowing the length of a train carriage and the speed of that train tell us anything? Well, very much the distance of that carriage is a bit like the distance of one wavelength. And we measure this and we give it the symbol lambda. Now the time it takes for one complete wave cycle, or one train carriage to go past, is what we call the time period t. Now before we said v equals x over t, but in one time period, capital T, one wavelength of a wave goes past. And we can then say that v is equal to lambda over t. We can also write this as 1 over t times lambda. So the velocity equals 1 over t times lambda. However, 1 over t, 1 over the time period, is equal to the frequency of that wave. So if we put this, we replace 1 over t with frequency, we can say that v equals f lambda. So v very furry lambs. And I did say that there are two equations before. I talked about the cute furry lambs as well. Well, this wave equation here, which is absolutely key, applies to any wave at all. However, there are certain sorts of waves that we know their speed. It's an absolute certainty. And this speed, we give the symbol little c. Little c is the speed of light, one of the universal constants. And if we're talking about electromagnetic waves, we can say that c equals f lambda, provided those waves are travelling in a vacuum, or something a bit like a vacuum, or close enough like the air. So the wave equation, the wave speed is equal to frequency times the wavelength, or the speed of light is equal to frequency times wavelength. But this one here is only for EM waves.